All right, well, let's go ahead and get started. So this is lecture number 19 for the Wireless Communications Lab. I'm Professor Robert Heath, giving the lecture. So today we are going to cover some material that is traditionally taught at the beginning of a wireless course. And this is, we're going to start talking about propagation and fading channels. And so why this is normally taught at the beginning of a wireless course is that this is one of the distinguishing features of wireless communication is the propagation environment. There's a lot of multipath, there's a lot of delay, spread, there's mobility, and it's one thing that makes wireless different from wireline communications. Why we are covering it now is because it doesn't really impact the design and implementation that we do in the lab. It's important for system design, but not as much for the signal processing aspects of what we do. So that's why we cover it a little bit later here. So what we're going to do is we are going to talk about, just propagation and fading. So I'll, define the mechanisms of propagation. And you should be able to define them as well and distinguish between large-scale and small-scale fading. And then second, what we're going to do is we're going to go into more depth on large-scale fading. And so this is going to involve calculating the received signal strength, the path loss, the received SNR as a function of distance from the Friis free space equation, log distance equation, and log normal Gaussian models. And then depending on how much time we have, I might also do a quick review of dB, dBW, and milliwatts and watts. Okay, so let's get started with the introduction to propagation and fading. Okay, so this picture for propagation and fading is going to start with us looking at sort of an abstract communication system model where there's a transmitter here. You can think about this as being like an access point or something. So maybe this is inside a room here. And there's a receiver, maybe this is a laptop here. See the laptop there with its little horned antennas on top, as most laptops have these days. And there's communication between this transmitter and receiver here. So let's call this transmitter, call this receiver. And these different paths between the transmitter and receiver, different propagation paths. These are different modes of propagation here. And there's usually one that we call the line of sight path. So this would be the path where the receiver can see the transmitter with no obstruction. So this line of sight. And then there also may be reflected paths. And then, besides line of sight and reflection, there might also be scattering. So scattering is also like a reflection, except that the surface is rough. And so there's a wave impinging on this surface here, but instead of getting out one ray out, we get the little spread of rays here. And so this is scattering here. And this happens when the surface is rough. So essentially, it's got to have roughness, which is like on the order of wavelength. Say protuberance is on the order of a wavelength. So a microwave signal that has, let's say, a 10 centimeter wavelength, all the materials in this classroom, like the wall, is going to act like a reflector, even though it's kind of carpeted and somewhat rough, because the carpeting is very small on there. And then finally, there's also two other modes of propagation. One is there's, potentially transmission through an object. And there's also diffraction, which is the bending of signals around objects. So the main mechanisms of propagation we need to be aware of is line of sight, reflection, scattering, transmission, and diffraction here. Transmission often is not included, but I like to put it here. Now each of these paths here has associated with it a different attenuation, because we know from basic what is this law here about reflection here? Is that Snell's law? I don't remember which law it is here, but essentially, whenever there's a wave impinging on a surface here, there's a part of it that goes through and a part of it that reflects, and this energy has to be the sum here. And so part of that energy gets transmitted or absorbed through the object, and some smaller fraction gets reflected. And then further, the path length of these reflected paths and the scattered paths are longer. So there's going to be some delay here of tau 1. There's going to be another total delay here of tau 2. All these scattered paths, maybe they have a delay of tau 3. There's going to be like a tau 4 here and a tau 5. So the paths have different attenuation and delays here. So let me, I guess, write some of this down here. First here, so we're talking about, this is the introduction to propagation. Yeah. Yeah, I think it tells us the angles that the reflection and transmission happens. As a function of, what is it, the permeability or of the material, permittivity? One of those. Yeah, whatever that is. Good. So let me summarize here the mechanisms. So transmission, reflection, scattering, and diffraction. And depending on the carrier frequency and thus the wavelength, these effects may become more or less important. So they're all a function of the carrier frequency here and the wavelength here. So let's see here. So effects depend on the carrier or equivalently the wavelength of the signal here. And some of these mechanisms here, like diffraction. So diffraction seems kind of esoteric, and really it is. It's this weird, physics property, but it's actually very useful. So in urban areas, especially those with tall towers, and the diffracted the signal is communicating like this. What diffraction says is that for any of these very sharp points, those sharp points act like a secondary source, and so there's an equation that will tell us, how that signal behaves. But effectively, there's a way to model signal propagation around sharp edges. Buildings have urban areas have lots of sharp edges. So diffraction is very important for coverage in urban areas. It's also, to a lesser extent, important for coverage in indoor spaces that have lots of hallways and doors at lower frequencies. This diffraction effect becomes less as the frequencies get higher. There's still diffraction, but it doesn't bend as much. And so if we were doing like millimeter wave, diffraction effect would be negligible. Transmission is a function of the medium. So if we have an access point outside this classroom, the amount of signal we get inside with the door closed will depend on the material properties of the wall and the door. There'll be some attenuation through those materials. The The scattering depends on the roughness of the surface and whether it's going to be scattered or reflected. Okay, so these are the mechanisms of propagation here. Now, what we want to do is, we understand that what's happening is that our received signal is being delayed and attenuated here. And so we can model these effects here most generally using some kind of a linear time-varying system, because in general these effects change over time. In the picture here, we could have this transmission and diffraction could be happening around me as I'm moving around. Scatterer could be someone walking by. So these things generally vary over time. And the channel propagation and modeling is all about modeling this time-varying impulse response here. So let me just put that down here. The propagation model will describe a behavior for this h of t comma tau. So we'll abstract some behavior of h of t tau here. And so we're going to use the model for various purposes here. So we're going to use models for, one is for simulation, two is for performance analysis, and I'm distinguishing between simulation and performance analysis based on this one is done on a computer, and this one might be done using mathematical expressions. And then we can use both of these to help in our system design. And we want to do all of this here because we do not want to design a wireless system that just works in this room that I've illustrated here. We want it to work in a lot of rooms. But we don't necessarily want it to work everywhere, because that might be too much of an unconstrained problem. So for example, we might want a wireless LAN to work well in office spaces and in homes, but we might not care if it works well in, way down in the berths of a large tanker ship that's got a lot of metal. Maybe that's not a priority there. It would be a lot harder to make wireless work in a big metal ship. So we come up with models that reflect the different set of possible propagation scenarios that we can see. Sometimes you're right next to the transmitter. Sometimes you're further away. Sometimes you're around the corner and you're getting a reflected signal. So the models are generally there to capture these different scenarios here. And so what we're going to do right now is we are going to work on building several simple mathematical models that capture different aspects of this channel here. We want to do things in a way that are going to allow us to do some closed-form performance analysis and also allow us to do some simulations. And then from both of these, we can infer properties of system design. For example, on the system design side, you might say, how many taps do I need in my equalizer? That's going to be somehow a function of the propagation environment. It's going to be a function of, how many different delays that I've got and how significant those different multipaths are. So we have a good channel model that will tell us, that will give us an idea about the parameters we might want to select for our equalizer. It's one of the things we're going to do here. All right, so that's just a little bit of background about propagation. Any questions about this here? Those of you who are listening on the recording, there's a huge number of students in the audience right now. It's not just two. Actually, it is just two. Either of you two have a question? No.
Are we going to worry about what happens when we get multiple copies of this class?
Multiple copies of what?
Of the same signal?
Yes. Yes. In fact, that's exactly what happens here, because what you see here is that we can get a signal from the line of sight path and a reflected signal. And so we're exactly going to worry about that. In fact, we've already been worrying about it because we have a channel that has multiple taps in it. So those multiple taps relate to the difference between this direct and this reflected path. So if you remember how we derived the complex baseband equivalent channel, we looked at the two-path channel. This is exactly the two-path channel, line of sight, indirect path here. But then we have to know, what's the difference between the two paths? And then what extra feature we're going to add now, so we want to get away from doing ray tracing. I mean, ray tracing, perfectly valuable area, but just not something from a signal processing perspective that we want to do. So we don't want to model the specific room, the geometry, where you're sitting, what all the seats are made of. We want to come up with mathematical models that approximate this environment, and by tweaking the parameters of the model, we can get this classroom, another classroom, a hallway, a dorm, by suitably tweaking the parameters of the model. And preferably there should be very few parameters, because we'd like to get some insight. If we have one parameter that we can tweak, then we can get some insight into the problem. Only at this point I forgot your question, so did I answer it along the way? Okay, somewhere in there, good. Okay, so now there's a whole body of literature devoted to propagation modeling. A big piece of propagation modeling is channel measurement. One of the ways that we learn about the channel is by devising systems that send training data and measuring those impulse responses. And we can measure them in a whole bunch of different places in this room. We can measure it in different rooms. And so that gives us data that we can use to build models here. So we're not going to talk about channel measurement itself. You all are already doing channel measurement in the lab, because when you have a transmitter receiver, you send the training, you're measuring the channel. So there's some other tricky approaches, but that's essentially what channel measurement's about. So what we're going to do right now is focus on modeling a particular quantity which is important, which is the average received signal strength. So that's what we're going to focus on the rest of the class. Oh yeah, and this is the large-scale fading portion here. Okay, so the motivation here is as follows here. So let's look at a system here where I've got a transmitter that's located at the origin. And I've got a receiver that I'm moving some distance away from the transmitter. Let's put the transmitter here at like 0 meters here. And let's plot the average received signal power as a function of distance d here. And so the average received signal power is going to mean the average in a location averaged over the area of several wavelengths. So I don't mean average in the sense of one point in time. I mean it's a spatial average here. And if we look at that here, so there's different ways. So first of all, if we just plot the measured received signal strength, what we're going to see is some equation, some curve that looks something like this here. There's a lot of variation here. And this is just the instantaneous received signal strength here. We're neglecting any kind of time variation in the channel, assuming everything in the environment is fixed. All we do is measure the location of our receiver here. And what happens is, there's different paths coming in from different places. Those paths have different phases. Sometimes they add up constructively, sometimes they add up destructively. And we get a lot of variation in that received signal strength here. So if we look at this here, so there's going to be a couple different characterizations of this received signal strength. So let's call this, maybe this is like, let's say 200 meters here, typical radius of a cell here. What we're going to do is we're going to first look at, okay, well, how does the average signal strength vary here? So what we're going to do here is we're going to look at this curve here, which is like the spatial average. And dealing with this spatial average here and the large scale, what we call large scale variations, that's what we're going to talk about now. And then, so let me put that in here. So this is like the spatial average of the received signal strength. And that may be actually too fine. So what we're also going to look at here is we're going to look at some sort of a more local average here, and then we're going to look at a very fine non-average signal here. So if we zoom in on the order of a wavelength here, so this is on the order of a wavelength, what we'll see is that the average received signal is roughly the same, right? Because it doesn't really matter where I am on my desk here. But I can hit that place where the wave adds up constructively or destructively. You know, if the wavelength is 10 centimeters and my desk here is easily, 1 meter by 2 meters, there's many places on the desk where it's going to add up constructively or destructively. But, I'm still probably 20 meters away from the access point at any given place. So this characterization of this fading here that's on the order of 1 wavelength here, this is what we're going to call small scale fading. And it's called small scale because it's on the order of a wavelength. And it's called fading because fade is like the, I don't know, where does fade come from? Fade. Used in a long time in audio here. I mean, maybe essentially a place where it's attenuated here. And then this characterization of this orange curve, and to a lesser extent the green curve here, we're going to refer to this as large scale fading. And this is going to be behavior on the order of tens or hundreds of wavelengths here. And in today's lecture, we focus on large-scale fading, and then in subsequent lectures, we'll talk more about small-scale fading. So what we want to do is we want to characterize the behavior of this orange, signal here. And some things that we can see, first of all, that it's decreasing as we get further away from the transmitter. And there's something intuitive about this here. Our antenna size is fixed. As we get further from the transmitter, that wavefront, which is transmitted with the same amount of power, is spreading and getting bigger and bigger here. So the further away we are, the smaller the piece of that wavefront we capture. That's kind of the less energy that we get here. So we kind of expect that it decreases. That would be sort of weird that we went further away and somehow it got stronger. Now there's, we can construct weird cases, but in general, this is what happens here. And then there's large objects, though, that might be in the environment. For example, like a building. And so these kind of large dips here are accounting for significant variations in the propagation environment due to like large objects. And then we call that shadowing here. So large-scale fading is going to be about this loss as a function of distance and about this variation, which is going to be shadowing. And this loss as a function of distance is what we call path loss. So it's about path loss, and that's about shadowing here. So just to summarize here on the terminology side, so small-scale fading is this, this super wiggly line here. The low part is a fade. Large-scale fading refers to this orange curve here. The dips in the orange curve are due to shadowing, and the average trend corresponding to the green curve is the path loss here. Okay, so now let's look at coming up with a received signal model here that will capture some of these effects here. So for the purposes here, so we're going to consider a characterization, like a narrowband characterization here. So we're going to consider, for now, a narrowband signal where this will make more sense, but essentially there's no intersymbol interference effect. So it's just like sending a single carrier, let's say. A model for the received signal power that we will often write here is something like this here, is that the received power is equal to some, let's see, okay, the received power at a given distance is equal to a product between a large-scale random variable, a small-scale random variable, and the transmit power. So this random variable here is going to represent this variation here about the mean. Large-scale random variable is going to represent this variation here around the mean. And so for the simple equation here, we assume that these quantities here are uncorrelated. Now, in reality, right, when you're behind a building for a while, so they're not really uncorrelated and independent of distance. But for the sake of this model, we're going to assume that. Now, this distance dependence shows up in a lot of different places here. So the very common way to write this here would be to look at what's called the Friss free space equation. So it would be the received power is equal to the transmit power times the transmit gain times the received gain divided by 4 pi lambda squared d squared. This is Friss free space. Actually, I said the hyphen there here. It's Friss free space equation here. And so that tells us that the received power is a function of distance. In free space, no obstructions, decays as the square of the distance. And this parameter right here, this is the wavelength here. So if we have a higher wavelength, we have a smaller received, sorry, if we have a higher, if we have a higher wavelength, smaller, let me think here. Why is this working here? Should be inverse wavelength. Yeah. No, but I mean, somehow if the wavelength, oh yeah, right. No, but if the wavelength is bigger, this quantity is getting smaller. Yeah, I'm just thinking here, I think let me see here. Yeah, it's on the it's on the top here. Yeah, if it goes on the bottom, we have, some other function there here. And I think this is a constant here as well. But yeah, this is correct here. This is done under certain assumptions that the antenna aperture is fixed as a function of wavelength. So the gains here, in some sense, are also a function of wavelength. But, assuming that those gains are fixed, then for smaller wavelengths, the received power decreases here. And as we go away with distance, the received power decreases here. So this is just an example of a relationship between the received power and the transmit power. Now what we want to do is we want to generalize this somewhat so that we have a contribution from a large scale effect and from a small scale effect here. Now I'm going to provide a little bit of background now before we do this here on, oh I see, okay, yeah. Yeah, I was just realizing I screwed something up here, but all right, that's all right. We'll get to it in a minute here. So I want to provide a little bit of background on the dB and dBm, dBw here. So let me just put, so this should be modeling, sorry, this is background on dBw, dBm, and dB here. Now because of this exponential dependence between the distance here and the received power, the received signal values very quickly get very small. So if we plot this right here, right, this will quickly go to 0 and we won't see anything interesting. A lot of times we look at received signal power in terms of dB notation here. So instead of writing this out in terms of linear here, we write this out in terms of the log scale here. So just as a quick review here of the dB scale, so some quantity x in dB, the way I'm writing this notation, so I'm going to try to put this little bracket here after the value if it's in dB, otherwise it's in linear scale, is just 10 log 10 of x. This is kind of the standard definition here of dB. Now, what we use a lot in wireless is this concept of dBw, or dBmw, or dBm here. And that is where we say a power in dBw is equal to 10 log 10 of the power in watts divided by 1 watt, or referenced to 1 watt here. The dB is a unitless quantity here, so we have to somehow get rid of the unit. And so when we write dBw, we're saying that this is basically, this power in dB is referenced to 1 watt. Because the signal powers are often, even in dB, still very small, we use yet another quantity, which is dBm. So power in dBm is going to be 10 log 10 of power in milliwatts divided by 1 milliwatt here. And so we actually often used dBm, at least in most commercial wireless systems, instead of using dBw here, because the powers that we're talking about may be 5 dBm or 10 dBm. You can go easily between the two, though. I mean, it's just a matter of looking at this equation here. So if I have power in dBm, I can get that from power in dBw by adding 30 dB, right? Because the difference between a watt and a milliwatt is a factor of 1,000 here. Now, the watt notation, so this use of dBw and dBm, dBw, the W often disappears. The M doesn't disappear, but the W often goes away, and it's okay. It's just, it's not always shown here. So let me point that out here. W sometimes just dB. Now let's look at the case where you scale the received signal by something here. So if I have that the received signal in watts is, let's say, alpha times the transmit signal in watts here, and I go through here and I want to determine what is this in terms of dBw here. Well, what I would do is I would divide both sides here by 1 watt, and then I could take 10 log 10 of both sides, and so then I could say the power in dBw is equal to, now look here, the watts only affect this term here. So we get 10 log 10 of alpha plus PT in dBW here. And so we might write this as alpha dB plus PT in dBW. And why I'm pointing this, equation here that you may have seen just years ago in circuits here is that this here is unitless. This is not dBW here. And this kind of made sense here because if I had like 1 watt and I multiplied it by 2 watts, I'd get 2 watts squared, which doesn't actually mean anything here. If you have an amplifier will take 1 watt and convert it into 2 watts. And that factor of 2 in dB would be 10 log 10 of 2, which would be 3 dB. So when you're doing these calculations, in the homework, and at least for this class, you should be careful to indicate when things are in dB, dBW, or dBm here, because it is an important distinction here. Okay, so that's just a little bit of review about dB here. So our large-scale path loss model, we are for the most part going to focus on building the model in dB here. So making something that's corresponds to received power in dB, not in the linear scale. So any questions about that here? dB? No. Good stuff. All right. Yeah. Yeah, so I'll get to that now here, the actual model. I realized I missed that. So yes, I got confused here. I went through 1 page of notes in the wrong order here. All right, so now we're actually going to talk about the large-scale fading model. Yeah, so yeah, here I have the Friss free space equation correct, which is the received power is equal to transmit power GT GR lambda squared divided by 4 pi squared d squared here. And the lambda over the d makes sense because we have meter squared over meter squared, so it cancels. So that's why I can tell that this is not totally incorrect. All right, now let's write this in dB. So in dB, we're going to get the received power as a function of distance in dB here. And I'm going to leave this generic, but let's call this, I'll just put dB here. And then this is going to be the transmit power in dB plus this gain, transmit antenna gain in dB, plus the receive antenna gain in dB, plus 20 log 10 of lambda, minus 20 log 10 of 4 pi, minus 20 log 10 of d here. Now, if I put this in dBm, what would change here? Only one thing. This PT would be in dBm, and the PR would be in dBm. Everything else would stay the same. So going from dB to dBm doesn't change the values of these quantities, only changes the transmit and receive coefficients here. So this first free space equation is good for free space, but unfortunately, terrestrial, wireless here, there's tons of junk everywhere. Free space is not a good model. So instead, so let me write that again, free space here. So instead, we end up looking at what's called the log distance path loss model. So the log distance model is an abstraction of this here. So what we see here is that there's a receive power, a transmit power, a whole bunch of constants, and then minus 20 log 10 of d. So the distance dependence only comes in right here. So the log distance path loss model says, okay, well, my receive power in dB is equal to my transmit power in dB minus L in dB, which is what I keep referring to here as path loss. And path loss is the loss in the system here it's kind of the negative of all the stuff we've added here. So, I mean, in some sense it should be path gain, but the gain is always less than 1, so we call it path loss and make it positive here. In the log distance path loss model, what we do is we write this path loss term here in dB as a function of 3 things here. The first one is what's called a reference distance. The second is an average received signal distance here. And the third is an large-scale random variable here. So let me write down what these different terms are here. So D naught is called a reference distance. And so this is a distance that's typically chosen to be close to the transmitter, but in the far field. But typically this is on the order of, it can be a wavelength away, but you might take this to be like 2 meters away from the transmitter or 5 meters, depending on the kind of system that you're working with here. It has to be in the far field because when you're really close to the transmitter, you get all these near field mutual coupling type effects, and that screws up this equation here. First free space equation is a far field equation. This LS of D0 is the loss at the reference distance. So this would be at that 1 meter away, you measure the average received signal strength. And that's what the LS of D here would be. If you're given this in a problem and you're not told what this is, then you use the first free space equation to find it. And then the third term here, so notice that this, if you were doing this in dBW, this would be dBW right here. This would be dBW. These other quantities here are going to be unitless. So is that correct? Not really. All right. The other quantities we have here, because this loss here, we have some meters somewhere that would have to be solved. But anyways, it gets absorbed in this constant here. So this other term here, L bar of D, this is the average path loss here. And then this would be given by 10 n log 10 of D here. So this is a log of the distance, but instead of having 2 here, we have n. And that n is called the path loss exponent. Most of the systems that we look at, that n will be somewhere between 1.5 and 5. Typical urban area, it would be 4, 4.5, maybe 3.5. In a very peculiar area, like in downtown Manhattan, it can be less than 2 because you have a waveguide effect. And in some places, it can be as high as 5. So this path loss exponent is a quantity that you would be given, and that would be derived from measurements. And it seems like that quantity is kind of innocuous, but there was a huge battle between the CDMA and TDMA when they were coming up with the 3G cellular standard. And the expressions for the capacity of CDMA depended very strongly on that path loss exponent. And so there were claims by the CDMA camp, of course, that it was very high, and claims by the TDMA camp that, no, it wasn't that high, and so the capacity was lower. So even though it seems like something simple here, tweaking that can have a big impact on system performance. The reason is that in cellular systems, they're interference limited. And so the larger this value, the faster the signal decays as a function of distance. And so your interfering signal has lower power because it's decaying faster. And so in systems that are very sensitive to interference, like cellular systems, having a big exponent here is good. But then if it's too big, that can be too optimistic and lead to incorrect conclusions. Okay, the other quantity that I haven't mentioned here is x of sigma. And this is a zero mean Gaussian random variable, not complex. We actually get to work with real one here. Zero mean Gaussian random variable with variance sigma squared. Now this is a Gaussian random variable in the log scale. And so sigma here is typically given in log notation. So this would typically on the order of 5 to 8 dB here. And so the parameters of this model here, so for the log distance model, we need the reference distance, we need the path loss at the reference distance, we need the path loss exponent, and we need the variance of this Gaussian random variable. And this Gaussian random variable here we refer to as large-scale fading. So the small-scale fading refers to the variation in short time scales. The large scale is the variation in larger time scales here. Okay, so that's like the log distance path loss model here. Now there's many extensions of this model here. So if you look in a typical cellular book, there's something called the HADA model. 802.11, N has its own model, etc. here. So typically what those models do is they end up with a formula that looks like this here, but it adds additional terms. Like maybe there'll be a term that's a function of the height of the transmitter or a height of the receiver or the carrier frequency. Right here we had a lambda term. We don't have one down here. And these equations are derived from measurement results. So someone would go out and do make measurements and have the antenna at different points on the base station, and then they would find that, oh gee, it looks like this would be a good fit. And so then they use statistical techniques to estimate the fit of those parameters there. And that makes sense because this model, we're trying to capture a whole bunch of different propagation phenomena, right? I mean, it's not just free space. There's trees, there's grounds, there's buildings, there's people. So there's a whole lot that's happening. We're trying to approximate all of that as one function that depends on distance. And effectively, we come up with a function that looks like this here, where this is a constant. This is this formula that contains a path loss exponent, and this is a random variable that accounts for the variation here. So we can add additional terms that are functions of other things in the system, and then correspondingly reduce the variance of this here. So that's the idea of the log distance path loss model. Now I want to draw this received power as a function of distance here. So this is distance. So effectively what this says is, first of all, this equation doesn't tell us anything that happened before that reference distance. Nothing happening there. And what it says is that the average characteristic behaves like this here. So that's going to be the L bar of D. This value right here is L of D naught. That's D naught. And then what's happening is that every point here, we're adding a Gaussian random variable in the log scale here. So we're sort of, at any given point, we're adding, some cloud of possible values here. And that's what we end up getting here. And that is not exactly the same as my nice smooth curve here, because I didn't capture the correlation that happens, as I mentioned, like you're behind a building for a while. But it gives sort of the same average variation here. Now, if we look at measurement results, and I didn't bring a paper that has them, but real measurement results have such a cloud. I mean, so you make the measurements at 100 points. They don't fall on top of this line. They fall all over the place, but they roughly decay with distance. And so effectively, this variance of this large scale parameter captures that kind of, what I call it, modeling error or fit. Okay, so any questions about that here? What's that?
There will be next Wednesday.
There will be next Wednesday?
Once it's on the test, and there will be in a few weeks.
Okay. Oh, I see what you're saying. Yes. So you will have questions after the midterm. Okay, got it. Got it. All right. 6. Okay, so one quantity that we will want to compute is the SNR, because as we've already shown, in systems where there's additive white Gaussian noise, the performance is determined by the SNR. A quantity in particular that we'll want to compute is the average SNR as a function of distance. And so that average SNR, we can write this as a function of distance in dB as equal to the received power as a function of distance in dB minus the noise power using the same dB. So if this is dBW, we can put dBW here. Doesn't matter here. These can be dBm, this can be dBm. They have to be the same, though, because you have to cancel them out, because SNR is unitless. And then, for the most part, you will use received power minus 10 log 10 of n naught, something like this, n naught times the bandwidth here. So the received power will be, sorry, there should be bandwidth there. So this would be the noise power, and this would be the received power here. So what you can see is that the SNR also varies as a function of distance. The only difference being the constant here. Okay, so the last part of what I'm going to do today is I'm going to do just essentially an extended example. And so I'll give some variation of this example on one of the homework assignments. Again, this will not be on midterm number 2, but will be on the final in some form, most likely. So let's go through now an example. So I'm going through this example just to show what we do with this information. I mean, we have a model for received signal strength, so what? So what can we do with it here? So let's look at a system here where I have a transmit power of 100 milliwatts. And that's equal to 20 dBm. I have a reference distance of 1 meter, and at that reference distance, the received signal power is 10 dBm. D naught is equal to 1 meter. My path loss exponent is 3, so I'm using the log distance model here. So let's go through some of the calculations here. So first thing that you might want to do is calculate the average received power at 100 meters. Now this seems like something reasonable. On average, 100 meters away, what's my power? So I'm going to use the log distance model here. So that is, now I'm going to calculating the average here. So I'm not including that large-scale fading, that Gaussian random variable, because that's zero mean, so I don't need it. So all I'm going to do is I'm going to look at this PR of D, and I'm going to compute this in dBm, equal to PT dBm minus LS of D naught minus L bar of D here. So if I've done everything correctly here, which is possible, LS of D0 should be really should be computing something like this here. T minus. Yeah, okay. I mean, doing something, the problem is this reference power here. I'm not quite writing the path loss correctly here. Because really what I should be doing here is computing. Yeah, all right. I'll hopefully this is correct here. But something strange bothering me about this example, but hopefully what I have in my notes is correct. So this is going to be equal to 20 dBm minus, so this is the confusing thing here is this LS here is 10. So I'm not sure how to deal with that here. Where did that go? Where's the dBm go? And then minus 10 times n times log of 100. So that should be equal to 60. So neglecting this issue here, which I'm a little bit confused about right now, that's going to be 20 minus 10 minus 60, which will then be minus 50 dBm here. So I think that's okay here. Oh yeah, where did I get the 10? Yeah, 10 was right there. Okay. All right, now, assuming that this whole thing here, this is correct here, now let's go through another calculation where we suppose that the variance is 8 dB here. And now what we're going to do is we're going to compute the probability that at 100 meters, my received signal power is less than minus 60 dBm here. Right, this kind of makes sense too because we are adding that random variable on top of this here. So we're not guaranteed to get a particular target value, but we can ask the question of how often it's really bad. And let's say suppose that it's minus 60 dB is bad. So we computed here that the average was minus 50. So now we're going to ask how often is it 10 dB below that? So that's effectively what we're going to do here. So we're going to compute basically the probability that minus 50 dB, which we just computed, plus x sigma is less than minus 60 dBm here, which is equal to the probability that this x of sigma is less than minus 10 dB here, right? So we move the 50 over here, dBm cancels to dB, we get minus 10. And then that's just equal to the probability that x of sigma is greater than 10. This is Gaussian, is symmetric. And then that is just equal to, whoops, let me go to the next slide here, 8. And that is just equal to the probability that x of sigma divided by sigma, which is 8, is greater than 10 divided by 8. And what happened here is by dividing by 8 here, I have created a Gaussian zero mean unit variance random variable for which we know the formula for the probability that x is greater than some threshold, which is just given by the q function. So that's just going to be the q of 10 over 8 here, which is equal to q of 1.25, which my computational sources tell me is about 0.106 or 10%. Now notice here, I've kind of gotten rid of the dB, but that's just because the whole thing is in dB scale, so we don't really need to care about the dB at this point here. This is all correct here. This makes it a unit variance Gaussian random variable. That's how we define the Q function. And then we just plug it into the Q function, or a table, or your calculator, and you get this answer here. So the conclusion is that under these assumptions, 10% of the time at 100 meters, the signal level falls below minus 60 dBm, 10 dB below our average, 10% of the time. That kind of makes sense, because 10 dB is more than one standard deviation away. So it does sort of work here. Okay, so final thing that we're going to compute is something slightly different here, is the distance required. So suppose that we have the following problem. What distance is required such that the probability of the received power as a function of distance being greater than minus 65 dBm is true 95% of the time. So before we plug and chug here, so let's think about what we're trying to say here. Is we're saying that, okay, I want my received power to be minus 65 dBm. Well, how we might get that is we might know that the noise power is minus 75 dBm, and we want the received power to be 10 dB above the noise power. That gives us minus 65 dBm. We'll actually do that calculation. I meant to do that calculation today, but I don't have the numbers here. And then we want this to be true 95% of the time. So what we're trying to do is we're trying to figure out how big can I make my service area here. So we're saying that my service area is good if 95 times out of 100 I can serve a power that's at least as big as this here. So it's just a way to define coverage. That's all it is here. Coverage being the area where we get sufficient received signal power. So I'm saying sufficient is better than this threshold 95% of the time. So given that, all we have to do now is we just have to plug in to this equation that we had before. So this is the probability that received power, transmit power, minus the loss as a function of distance, minus 10n log 10 of, oh, what have I done here? D over, I forgot the D naught here earlier. Oh, man. D. Shoot. Yeah, this is why I was the units here were bothering me here. I have to divide through by that reference distance here. That gets rid of the meters. Okay. Oh, sorry about that. All right, so now transmit power minus reference distance power minus 10 log d over d naught here. Plus this random variable x of sigma should be less than minus 65 dBm here. 95% of the time. So that should be equal to 0.95 here. So the only random variable is this x here, so that's equal to the probability, and we're going to go ahead and divide through by sigma. So the probability that x over sigma is greater than 65. So I'm going to do greater, so I'm going to flip the sign here. So 65 plus pt minus this reference distance loss minus 10n log of d over d naught divided by sigma. I'm going to let that equal to 0.5. So instead of computing the probability this is less than, I'm going to compute the probability that this is greater than 5% here. And so then you can go through here and find that the Q of alpha, set that equal to 0.5. Alpha should be equal to 1.65. So then we say, okay, 1.65 sigma is equal to 65 dBm plus PT minus Ls of d naught minus 10n log 10 of d over d naught. I picked d naught to be 1 meter, so it doesn't matter here. We go through and plug all that in. We'll find the distance is about 114 meters, if I did this correctly. And so then we can say that our cell edge is, our cell can support roughly, a communication range of 114 meters away. We can guarantee this received signal power 95% of the time. Yeah, I suspect the calculation, I suspect that number is actually wrong, because it should be smaller than 100. Let me think here. Yeah, I probably have to recheck the actual numbers here. I think it should be a little bit smaller here. But that's the idea here. So that's 3 things that we can do with this model here. Compute the average received power, compute the probability that that power is greater than or less than some threshold, and then determine the distance such that the probability is greater than or less than some threshold here. So we can use this to approximate the average phase signal strength, and then to give us an idea about the transmit-receive distance that our system can support. Okay, so let's go through this real quick here. We talked about, the basic concepts of propagation and fading. So you should be able to define these different mechanisms and distinguish between large-scale and small-scale fading. And so the important points there is distance-dependent path loss, the large-scale, the small-scale, things vary as a function of distance. That variation depends on the wavelength. Are we looking at fractions of a wavelength, many wavelengths? And then we took a side detour here in the review of the dB, dBm, watts, and milliwatts. So you should be able to do these calculations there. And then we concluded with this discussion of the most common large-scale received signal models, the Friis free space equation and the log distance path loss model. And so you should be able to calculate the received signal strength, path loss, received SNR, as a function of distance, using these different models here. And yeah, so that's it here. Any other questions? What's that? Yeah, okay, so your question is, can you leave the answer in the Q equation if you don't know?
Like when we get to a test,
Yeah.
we can't use calculators.
Right. So I would have to give you some means of calculating that for that to be interesting. So I could give you a table, for example. Kind of like the old.
That's a pretty big table for me to write down my notes otherwise.
Yeah, I ask for a lot of things, but I don't ask you to know the Q function or write its table down. So if I didn't give you the table, you just leave it in terms of Q. Yeah, that's a good question. I'm not totally unreasonable. Just because I ask people to remember Fourier transforms, I'm labeled as a unreasonable person. All right, any exam-related questions? Okay, but you'll get those when you're taking the exam, so then I won't be able to help you.
Unfortunately.
Yeah. Okay, well, I guess people will be listening to this on Monday, and so hopefully if you're listening to this, and it's before the exam, you know that there's an exam next Wednesday, and you're preparing for that exam. And you can have, I forgot to mention this, but 2 pages, handwritten notes, front and back. That's your own handwritten notes, not a copy of your handwritten notes, not writing your notes on the computer and printing them out. That's written by hand. All right, that's it.